Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 2 of 4 on the topic of index flood regionalization and will cover an introduction to L moments. Let's get started. In our regional frequency analyses, especially for precipitation, the statistics of the sample and the population are measured in a different way than what we use for streamflow frequency analyses. In this video, we will explore L moments, an alternative way to characterize the statistical properties of our samples and populations. But first, let's take a look back at product moments, which we've seen several times already. Product moments are used to summarize the properties of a sample or a population by quantifying their central tendency, spread, asymmetry, and peak and tail weight. The formulas for the first 4 product moments, mean, variance, skew, and kurtosis, are shown here. The key to each formula is that as the moment gets higher in order, the power of the deviation of the mean gets higher. This change in order allows for varying parts of the sample to contribute differently, making it possible to quantify these different shapes to the sample. The key thing to keep in mind is that product moments are characterized by these powers of deviations from the mean. We will see shortly that this can lead to problems in using sample moments to estimate population moments. 2 studies in 1974 using Monte Carlo simulation studied the properties of product moments and their utility in estimating the population properties of a sample. The Monte Carlo simulations in these studies started with the known population and drew large samples from the known population. These samples were used to compare how well these subsets were able to be used to estimate the original population parameters. The authors found, in their words, unexpected and profoundly disturbing results. In a population with a skew of 5, which is a large value, none of the samples they drew from the population had a skew greater than 2.67. When they increased the population skew up to 15, which is extremely high, the only result they saw was that the discrepancy between the population and sample grew. This poses a serious problem when our goal in frequency analysis is to use the sample of data we have to estimate the properties of the population that we can't see. Specifically, what this study found is that the samples we take from a population have a bound that has nothing to do with the true population value. For example, a sample coefficient of variation can never be larger than the square root of the sample size minus 1, no matter what the population coefficient of variation is. The skew and kurtosis suffer from similar issues. What this means for us is that using these measures potentially introduces bias and error, especially when our sample sizes are small. This is even more consequential because, as we've seen before, the population skew is already difficult to estimate from a limited sample size. We see that skew is very sensitive to sample size and can vary considerably with additional observations, and that outliers can disproportionately affect the estimate. On top of that, we may not even be able to achieve the population skew in a sample if the sample size is too small. As an alternative to conventional product moments, another way of measuring the shape of a sample or populations was introduced by Hosking in 1990. Linear, or L moments, estimate the same properties of a sample as conventional moments, except they use linear combinations of the observations instead of taking higher powers. The general form of L moments is shown here. The terms to the left of the X are used to emphasize different parts of the sample in order to quantify its properties, instead of taking higher powers of deviations from the mean, as in product moments. Here are the equations for the first 4 L moments. Libraries in R are available for computing the sample L moments, and HEC SSP can use L moments in its distribution fitting analysis. This makes computation much easier. The first L moment is the same as the product moment, and it's the mean, and it's computed the exact same way. The second L moment is where it changes from product moments. L2 measures dispersion without squaring the observation. L3 measures asymmetry in the same sort of way that skewness does, but does not cube the observation. Finally, L4 is a quantification of the weight of the tails and the peak of the sample. This schematic from Hosking and Wallace 1997 shows how each observation in a sample, n equals 19, contributes to the first 4 L moments. Each observation for L1 is equally weighted and positive, which is exactly how the mean works. For L2, you can see how observations further from the middle contribute more weight, which measures how the data is spread out. L3 and L4 are a little harder to interpret, but these weights help quantify the asymmetry and the tail weight of the samples. When we use L moments, typically we summarize them with some dimensionless quantities called L moment ratios. They are much easier to work with and especially to regionalize because they don't have units associated with them. This is similar to the coefficient of skewness or kurtosis with product moments, which don't use units. Dispersion is summarized with the LCV, which is similar in principle to the regular coefficient of variation that we saw in exploratory data analysis. It has values between 0 and 1 for data that are positive. It is computed as L2 divided by the mean. Asymmetry is summarized with L skewness, which is the ratio of L3 to L2. It has values between -1 and +1 with the same convention as product moments. Negative values indicate a left-skewed sample, and positive values indicate a right-skewed sample. Peak and tail weight is summarized with L kurtosis, which is the ratio of L4 to L2. It also has values of -1 to +1, with the convention that the uniform distribution has an L kurtosis of 0. Here are two samples to briefly illustrate the comparison between the two measures. For both samples, we find that the central tendency measured by both product and L moments is the same value. The sign of the skewness is what we would expect as well for both measures and samples. The key here is that except for the first moment, there is no direct way to go between these two measures. They can't be converted. This is because they quantify the properties of dispersion, asymmetry, and peak and tail weight in different ways and have different scales. So why do we introduce L moments in the context of a regional frequency analysis? Tradition is part of the reason. L moments have been used with great success in many large-scale regional frequency analyses such as NOAA's Atlas 14. Hosking and Wallace choosing L moments for their 1997 book is a large part of it too. However, it's not just tradition that drives our use of L moments. They have several statistical and mathematical properties that make them very attractive in a regional frequency analysis. First, they're robust to some of the problems that we see with product moments, and several studies have shown this. Their dimensionless nature makes them easy to compare across a large number of sites. When we want to analyze the uncertainty in a sample L moment, we find that their uncertainty distributions are normal, a property we don't have in product moments. And finally, we have robust methods for estimating population probability distribution parameters from L moments, which helps us build our regional models. The key to the regional analysis is that we will find that homogeneous regions of observations will have similar L moment ratios for their annual maximum or partial duration series. This lets us do two things. One, it helps us identify what the probability distribution for the region is, and two, identify if our region is truly homogeneous or not. In this video, we discussed L moments. 3 key points to take away from this video are: L moments are a method for quantifying the shape and characteristics of a sample or population that are a robust alternative to conventional product moments. L moment ratios are a dimensionless measure of the same properties we typically measure with product moments, and in a regional analysis, we expect sites in homogeneous regions to have similar L moment ratios. Thanks, and tune into the next video in this series on index flood regionalization to learn about estimating regional probability distributions.